So, now we will see the heat conduction through various type of conductors. First, again we have in the previous session we have seen the spherical conductor, the cylindrical conductor. Now, we will see the heat conduction through spherical conductor with constant heat production, as well as through the cylindrical conductors with constant heat production. Then we will see some series and parallel combination of resistors and network analysis through this heat conductors. So, now let us take the example of again the spherical conductor with constant heat production also. So, here I have a spherical conductor. So, this body, this entire sphere is a solid body whose conductivity is K, and in the entire body the heat is produced at a constant rate of P. So, thermal power generated inside the bulk is P, and outside the temperature is T naught. So, outside the steady state temperature is T naught. Let us find the temperature distribution inside this. So, we have a spherical conductor in which the power that is the thermal power is generated throughout the bulk at a constant rate P. The outside temperature is T naught and its radius is R. So, let us find the temperature distribution inside the sphere. So, now in order to find the temperature distribution, we have to use the Fourier's formula, that is the rate at which the heat is produced is equal to minus K into area through which the heat passes and into temperature gradient d theta by dx. So, this is our Fourier's formula. This will be used to solve this. Now, let us take a concentric region. So, we have taken this region. This is an annular region, concentric shell. I shade it, and let us see what is the rate of transfer of energy through this region. So, what we do, consider a differential spherical shell of radius x and radial width dx. Now, at steady state the heat generated inside it must be transferred through it. So, the heat generated dq inside delta q inside is the thermal power P into the volume 4 by 3 pi x q. So, this amount of heat must be transferred through this section. Now, you see the total heat generated is equal to 4 by 3 pi r cube, this is the volume into P. This much heat must be rejected from the outside, must be conducted from the outer. So, this much quantity per unit time must be transported. So, this is the power, that is the energy transported. So, I have got I, that is heat current, must be 4 by 3 pi r cube into P. P is power. Power means the amount of energy produced per unit time. So, that is dq, that is amount of per unit volume by time. So, total amount of energy that must be transported through this outer radii is this much. This is the heat current. Now, using the Fourier's law, that the rate of heat transfer dq by dt is equal to minus k A into d theta by dt dx. For this cell, the rate at which this shell must transfer energy is the rate at which the energy is produced inside it, that is 4 by 3 pi x cube into P. This is the same quantity dq by dt minus k area. What is the area of cross section through heat enters, that is 4 pi x square into d theta by dx. So, here we will bring all x this side. So, we have 4 by 3 pi p into 4 by 3 pi, this x cube x square. So, this is x dx is equal to minus, this is again 4 pi k d theta. So, here 4 pi cancels out. So, we have p by 3 x dx is equal to minus, this 4 is cancelled. So, this is only k left out d theta. We integrate it now. The limits is when x is x, theta is theta. When x becomes r outer radii, then angle, then the temperature is theta naught. So, this is p by 3. This is integration of x is x square by 2 from x to r, limits is equal to minus k T naught minus theta. So, this is p by 6 r square minus x square is equal to minus, we can bring inside. So, k I will bring here. So, minus T naught plus theta, k has been brought here. So, we have theta becomes T naught, theta becomes T naught plus p by 6 k into r square minus x square. This is theta. So, this is how the temperature will vary in the entire sphere. The highest temperature will be when x will be 0, that is T naught plus p by 6 k, and the as you go on the temperature will decrease and the least temperature will be on the surface, that is T naught. Take one more example of cylindrical shell. We have a cylinder in which there is a constant heat production throughout the material. So, if we have a wire in which current is flowing, then heat is produced throughout the wire. So, this is the cross section, this is the circular portion. So, I am just drawing the cross section of a cylinder of outer radius r, and the temperature outside is T naught, and inside the bulk throughout we have a thermal power generation at a constant rate of P. So, consider a cylinder in which there is a constant thermal power generation P. The temperature at the outer surface be T naught, the conductivity of the medium, the conductivity, that is the thermal conductivity of the medium is K. So, now what we do? We consider a annular region that is the cylindrical shell whose radius is x and this radial width is dx. So, I just shade it. So, consider the heat transfer radially across a differential cylindrical shell of radius x and radial width dx. So, we are again going to use our Fourier's expression, that is dq by dt is equal to minus Ka d theta by dx. dq by dt is the rate at which the heat is going to be transferred. This is given by this law, and at steady state the element, the differential element must transfer the heat produced inside it. That means, whatever the heat is produced inside the cylinder, that must be transferred outside through this area. So, let us apply this. Now, dq by dt is equal to minus Ka d theta by dx. So, suppose here the temperature is theta and here theta plus d theta. So, the rate at which heat is produced inside is the volume inside it. The volume inside is pi x square, that is the cross section area, into L into P. This is the rate at which heat is produced and this must be transferred, that is minus K. The cross section area is 2 pi r into L, through which the heat goes out, and d theta and dx, this is the temperature gradient. Now, we will, this is 2 pi x. So, this 1 x and this pi and this pi cancels. So, here 1 L and this L cancels. So, here P into x and then this bring this dx, and that will be minus 2k d theta. If I put the limits, then x, when x is x, theta is theta. When x becomes r, this is T naught, the steady state temperature on the surface of the cylinder. We carry out integration, P is here, I can bring 2k here, and then x means x square by 2, I have r square minus x square by 2, that becomes, this minus sign will go. So, minus I will get T naught minus theta. So, here P by 4k r square minus x square is equal to minus T naught plus theta, implies the theta as a function of x becomes T naught plus P by 4k times r square minus x square. So, you see, this is how the temperature variation will be there in a cylinder when the heat is produced throughout the bulk. So, now let us consider another different type of resistor, a cylindrical heat conductor with variable cross section. So, tapered cylinder we can say. So, here I have a cylinder So, you can see here this area of cross section, the radius is increasing. So, these are circular ends, I am just drawing the cross section. So, here this radius is R1 and here it is R2 and this length is L. So, during L length R1 changes from R1 to R2. So, the material has a conductivity K and this side is maintained at temperature theta 1 and we have this side maintained at temperature theta 2, write it here theta 2. Now, we have to calculate what is the net heat flow through this rod. So, what I will do? So, at a distance of x, I will consider a strip and you see this width is dx. So, at steady state what heat flows from here has to pass from here and has to pass from all the sections. So, I must know then the geometrical properties of this element. So, let us write first, consider the heat flow through a cylinder of constantly varying cross section area, cross section. Now, as seen this R1 varies to R2. So, let us see how first of all this radius varies. So, this is R1 and this is R2. So, I can write this as R2 minus R1. So, this one will become R1. So, at a distance x, you see this will be R1 here to here and you see this triangle, suppose this is y, I can write this by similar triangles R2 minus R1 by total length L is equal to y by x, implies y is equal to R2 minus R1 by L into x. So, thus you see here this radius R, the radius here R will be this y plus R1 plus this y, that is R2 minus R1 by L into x. This is very important point, the radius at this element. So, now you see here we have consider a differential strip at a distance x with distance at a distance x and width dx, that is thickness or width, anything we can say dx. So, now let us apply the conduction formula, that dq by dt, that is the thermal heat conduction, is minus k into d theta by dx. So, let this side the temperature be theta and this side theta plus d theta. So, we have I, that is minus k, a area means pi r square into d theta by dx, dx is dx only. So, now let us handle this equation which we got from Fourier's law of steady state heat conduction. So, now you see here we will bring this I here, I into dx by r square, that is minus k pi d theta. So, now let us substitute the limits. Here the variable is x. So, when x is 0, theta is theta 1, when x is L, theta is theta 2. So, this integration I 0 to L dx by r square. We will substitute the value of r, that is r 1 plus r 2 minus r 1 by L into x whole, that is whole square is equal to minus, this is k pi, this integration theta 2 minus theta 1. So, now you see this is a square here, something this integration is of the form of this, which is minus 1 by x. So, minus 1 by r 1 plus r 2 minus r 1 by L into x, and the limits from 0 L to L minus k pi theta 2 minus theta 1. Now, you see this is x square, but here there is a function of x. So, its coefficient must be divided. So, r 2 minus r 1 by L. This minus minus cancelled, I have I L, that is r 2 minus r 1, then we will first put L, L cancel, r 1 cancel, I will have I 2, then minus 1 by, we will put 0, we will get r 1, k pi theta 2 minus theta 1. Now, here I L by r 2 minus r 1, then this is r 1 r 2, then this is again r 1 minus r 2 is equal to k pi by theta 2 minus theta 1. So, I want my heat current I. So, you can see again this r 1 minus r 2 and r 2 minus r 1 gets cancelled, but there is one minus. So, I have I L by r 1 r 2, I will put this minus here, that is k pi theta 1 minus theta 2. Now, this becomes positive because heat flows from higher temperature to lower. So, I will be k pi r 1 r 2 by L into. So, thus this is the rate at which heat is transferred from this truncated or non-uniform cross section or uniformly varying cross sectional cylinder.